Right then, guys, just go off that. Okay, this is 1D. It's 1D from the IB AA Maths course from the Oxford book. Okay, so we've got a couple of investigations before 1D. And previously, of course, we've done work on sequences and series, and 1D is the last amount of work that we're going to do on this, and it's problems in context. So we're talking about either geometric sequences or arithmetic sequences, GPs or APs, in context. So a lot of words. Some of these questions will take quite a long time to read through and figure out what's happening and what bit of maths to apply in each case. Now, the investigations are really useful to do. So there's investigation 8 and investigation 9. Let's just go down here as well. They're really useful because you kind of learn through as you do each of those parts, and it kind of takes you through slowly. I'm not going to do them now. I'm just going to focus on the examples from the book. So I'm going to do example 26 and example 27. There are only 2 examples here, but they're quite long each. After that, there's 10 questions in the exercise. Right, without further ado, so I started this one before I kind of messed up, so just get rid of everything. Okay, so I want to do a perfect one take. Okay, right, so let's get rid of me. Let's hope this one goes well. Okay, so example 26, let's just read it through. It says, the number of Facebook users at the end of 2008 was 145 million and growing at a rate of 3% per week. At the end of 2010, the number of Facebook users was 608 million. A lot of information there, some of it useful. Let's look at A. It says, if the rate of growth has remained constant at 3% per week, determine the number of users at the end of 2010. Now, typically when I read these questions through, I would probably stop there and I would wait until I get to the next part before I read that one through. That's what I'm going to do here. I would normally need to read this through a couple of times as well before I've really understood it. So this time when I read it through, I'm just going to highlight the important information. And here it says the number of Facebook users at the end of 2008. So end of 2008, that's the same as the start of 2009. It was 145 million, growing at a rate of 3% per week. At that point, it's growing at 3% per week, but it doesn't tell us that it's growing constantly at 3% per week. That turns up later. Okay, and it says at the end of 2010, the actual data for the number of Facebook users was 608 million. And it also does say the end of 2010. So between these two dates, there's 2 years. And because we're talking about growth rates per week, that's 52 weeks in a year times by 2, we've got 104 weeks here. Okay, so part A then wants us to check this number here. So let's just check again. It says, if the rate of growth had remained at a constant of 3% per week, determine the number of users at the end of 2010. So it wants us to check this value here. It wants us to check the 608 by using our knowledge of sequences. Okay, well, hopefully you can see this is a geometric sequence because any essentially compound interest formula would be timesing by our 1.03. That would increase our amount by 3%. So it would give us 103%. Timesing by 1 obviously just gives us the whole amount. Timesing by 1.03 increases something by 3%. But we want to do that every single time, every single week. So if we want to do this for 104 weeks, then we're going to need to times by 104. So this is going to be 145 times by 1.03 to the power of 104. Now, I haven't set up a function here. I haven't set up un equals, although I could do. I could say this is un equals 145 times 1.03 to the power of n. Now, that's slightly different to the normal geometric sequences because normally we would write n minus 1. But in this case, the 145 is in week 0. That's right at the start. So week 1 after 1 week would be here. So the first value is going to be timesing by 1.03 to the power of 1. Okay, so I don't need the minus 1 here because my first week isn't the 145, it's this value here. Okay, so I'm kind of overcomplicating things a little bit here. We don't really need to write this down, and we don't really need to define this as a geometric sequence, although we can see that it is a geometric sequence because of the fact that it is increasing by a multiplier as you go from weeks to each week to the next week. Okay, so if you do this one, I think it turns out to be 3 billion and something or other. Okay, when I was just looking a second ago. So 3 billion and something or other is way off this value here. So this is not a particularly good model. It shows us that the 3% that it was increasing at, which is massive, by the way, at that particular point at the end of 2008, declined during the period. So this was only 3% of the week per week at the start. Okay, let's just have a quick look at what the answer was, in fact. So the answer was approximately equals to, so we're looking down here, this bit here, take it. You see where my pen is flashing? 3,136 million. Okay, so they've come up with, in fact, let's just take that back. 3,136 million. Okay, so that's in fact 3,136 million. And we've got approximately equals to there because presumably there were some other numbers here, but we just got rid of them. Now we're answering consistent to the question there because the amount of significant figures that we've given here are 4, but we're basically giving answers to the nearest million because the question is in nearest million as well. So I mean, obviously there wasn't exactly 145 million. There could have been, but it's very unlikely that there were. So because the numbers have been rounded off here to the nearest million, we'll round off our answers to the nearest million as well. Okay, so that's the first one, which is done. That's good. And for part B then, it says the growth rate of 3% per week remained steady for 6 months and then dropped to 1.1% per week. This growth rate was maintained for another 6 months, but then it dropped to 0.75% per week. Assuming that this rate was sustained for the entire year, for the whole year, show that this model better describes the recorded numbers. Okay, right. So we've got 145 by 1.03 to the power of 26, that's half a year. And after that, we're going to increase by 1.1%. So obviously that's going to be 1%, and then the 0.1% is going to go to the next decimal place. That's going to happen 26 times as well. So times by 1.011 to the power of 26, and then times by 1.0075. So that's increasing by 0.75% there. And that's going to happen for the last year. So that's going to happen for 52 weeks. Now, if you work that out, you will get your estimate in this case for the total number at the end of that period. And I believe it was 613 million to the nearest million. Okay, we've got this kind of wavy equal sign, meaning approximately equals to. Sometimes you might see in some books they do this kind of little bridge. That could also mean approximately equals to as well. But it's most common to use this symbol. Okay, let's just look at that answer as well. So we've got, yes, 613 million. You can see they've actually done it in steps there, and they've come up with these intermediate answers as well. So we've got 313 is where we end up with at the end of 6 months. So we've got 313 million, and then we've got 416 million, and then 613 million. Okay, good, done. So next part of the question. Oh, by the way, I made something up on this on Desmos, which I'll talk about in a little while. So I've made this model in terms of graphs. We'll discuss that right at the end. Okay, so it's a little extra. And it's kind of interesting because what I've essentially made here is a piecewise function. These kind of things will be useful for your coursework. So I'll do that at the end after example 27. Okay, part C, it says if the rate of growth drops to 0.6% at the beginning of 2011 and remains steady, determine how long it would take for the number of users to reach 1 billion. Okay, so at the beginning of 2011, we know that's the same as at the end of 2010. We definitely know we have 608 million users. So we've got 608 million users. The growth rate is now less than 1%. So we're going to go to 0.6%. And we want to know how many weeks it takes. So how many weeks after the start of 2011, how many weeks it would take in order to reach 1 billion. So 1 billion would be 1,000 million. Now, because we're talking about in terms of millions, we're just going to write the answer of 1,000 at the end here. Okay, now if you want, you can change this into millions by putting on 6 zeros. You'll need 6 zeros there as well, but essentially we've divided both sides by 1 million, and it keeps the equation in balance. We are working in terms of millions. Now, if you remember from last time round, the last video I showed you how to do logs to answer this. You can answer this with a table, but I showed you the example where I said 10 cubed is equal to 1 million. And in terms of logs, that would be the same as me writing log to the base of 10 of 1,000 is 3. And it's basically asking the question, log asks the question, and this here is saying, what power do you need on 10 to get the answer of 1,000? And the answer to that question is 3. So it's logs are the undoing function of powers. Okay, so we can put this in a similar form. So if we divide both sides here, to start off with by divided by 608, we've now got the same form as this here. And so we can use this format here in order to answer our question. So we can say log to the base of 1.006, that's our base number here. To get the answer of 1,000 divided by 608, what power do we need on this? It's the question that log is asking. And I don't know what the answer is to that, but if you type it into a calculator, then you will get the answer. Alternatively, you can do this by a table. Let's just have a little look at the answer. And yeah, the book I think has made a mistake. And this is common in the first editions, which this is just a PDF of the book. I think that the book has made a mistake in that it started with 613 instead. You can see they've set up the same formula here, but they've started with 613. But remember, the question says, if the rate of growth drops to 0.6% at the beginning of 2011 and remains steady, determine how long it will take for the number of users to reach 1 billion. Well, you can see they've used the number of users from the model being 613, but in fact, we know that exactly 608 million users were, there were 608 million users at the start of 2011. So it's better to use the original number. So I've used 608, they've used 613, but the method that they've got is kind of similar. They say 82 weeks, so from typing this into the calculator, you'll get an answer which is similar to this. Perhaps it will take slightly longer. So maybe it will take 84 weeks or something. Okay, let's look at the next question then. Example 27. Let's just take this. Okay, so this could be a geometric sequence question, or it could be an arithmetic sequence question. I don't know, but let's read a little further. So it says, when Jacob turned 18, he had access to the money his grandparents had invested in a savings account. Okay, there's not a lot of maths information in that case, just the fact that he's 18 years old and he's at the start of 18 there. He decided to reinvest $10,000 at a compound interest rate of 3%. $10,000 compound interest rate of growth of 3% each year. He decided to add $200 to the investment on each next birthday. So at the age of 19, he would be putting in $200 for the first time. And each following birthday, so then that happens again at the next birthday and the following one, until he turns 25. Evaluate how much money was in his account just after his 25th birthday. So that would include the amount which he puts in when he turns 25. Because just after his 25th birthday, he will have put that $200 in as well. Now it says, evaluate the total interest gained over this time. So we're not interested in the total amount, but we're interested in the total interest that's gained once we take away all of the money that he's put in. So once we take away the $10,000 and all of the $200, how much extra had he gained? That's how much interest he's got. Okay, so where to start? Well, I suppose from my point of view, the $10,000 is kind of separate. And I might actually, just to get a sense of this, I might in fact just think about how many years there are, because there's few enough years here to actually write it out. And a lot of the problem with these questions is to think, how many gaps are there here? Have I counted the number of years right? Because obviously 25 take away 18 gives us 7, but is there 7 years, or are there 7 gaps? Are there 8 gaps? Yeah, there's a real problem with overcounting the number of years here. Now, because the number of years are quite low, I might actually just write this one out, just to be really clear in my mind what's going on here. Okay, 22, 23, 24, and start of 25. So we can see at 18, we're putting in, not 20,000, 10,000. Okay, and that 10,000 needs to go through many months. In fact, it needs to go through, this is pretty basic here, guys. It's like me counting on my fingers. It needs to go through 7 jumps to get to how much is going to be there at the start of the 25th year. Okay, so 7 jumps there. Okay, now, in that case, that means we're going to have 10,000 times by 1.03 power of 10. And I think that's separate from the rest of the question, which is talking about adding the 200 each month. So I think that's kind of done. We can kind of separate that. And then we can talk about the 200. Because, you know, if we add in the 200, that 200 will be gaining interest of 3% per year, just as whatever was at the end of the first year there will be gaining the 3% per year as well. So I can separate the 2 out. It doesn't really matter. Okay, so I'm putting in 200 at 19, I'm putting in 200 at 20, I'm putting in 200 at 21, and so on. Now, at 19, I'm only going to have 6 increases from 19 to 25. That's the 6 gaps there. So I'm going to times by 1.03 to the power of 6. And the $200 that's put in at 20, age 20, is only going to have 5 increases. And likewise, the next one is only going to have 4 increases, and so on. Down to the last one is going to be put in as just 200. Oh, and the penultimate one was 200 times by 1.03 to the power of 1. Okay, so stuff which is missing there. But ultimately, what we want to know is what are all of these things added together. So that's the sum of a geometric sequence which we need there. Okay, now you can see this is not a formal way of writing things down. I'm just trying to visualize what's happening here. And it's the fact that there's few enough years means that I can put down my thoughts on the page here. Because I think this is quite a difficult question to analyze what is going on and what's happening to each of these things before you come to that realization that this is the sum of a geometric sequence. Okay, right, I'm going to get rid of all of this just to give myself a bit of extra space. So we had now 10,000 times by 1.03 to the power of 7. And then we had the sum of, I can actually write it in sigma notation here, from 1 to, now there were 7 things that I was adding together, remember. So I was doing 200 times 1.03 to the power of 6 all the way down to 200 times 1.03 to the power of 0, if you like. There was 200 put in on the 25th birthday. So that's going to give me 7 terms. Okay, so there's 7 terms there. And I've got 200 times by 1.03 to the power of n minus 1. Okay, so the terms are back to front. We would normally sum the geometric sequence from the 200 to the 200 times 1.03, 200 times 1.03 squared, and so on. Normally do it that way around, but they're back to front because the 200 is in fact the last amount which is put in, not the first amount which is put in. Okay, right, so this is the sum of what I need. Seems to me like I can just use a formula now. And the formula, remember, which we use for the sum of a geometric sequence is going to be a times by r to the n minus 1 divided by r minus 1. A is 200, r is equal to our rate. So it's not a 3%, we're not putting in 3 as the rate, we're putting in 1.03 because that's our common ratio, our multiplier. We have 7 terms, okay, from 1 to 7, take away 1, and we have 1.03 there, take away 1 on the bottom. Now, once we've got that, that's going to be the total amount of money in the bank from all of the $200, $200, and we'll have the total amount in the bank from all of this thing here, from the $10,000. And then once we get those two answers, we can sum those, and then we can take off all of the money which we put in the first place, because we're only interested in the total interest. So we'll need to take away the 7 amounts of $200 and the 10,000. So 7 lots of 200 is 1,400. So we'll need to take off this amount of dollars at the end. So this will be the final step. Okay, let's just check the answers there. Let's see if I've done that one right. What have they got? Yeah, they've kind of done it in the same way. You can see that when we've got down here, they've got 12,298.73. That comes from 10,000 times 1.03 to the power of 7. So they've separated that out. I don't particularly like the way they've started this. If you read just where it says just after his 20th birthday, they've tried to put that in maths. I think that's quite difficult to read without explanation. So sometimes reading maths is really difficult without thinking about it yourself first and trying to construct it yourself. I like what they've written in the first equals line there, where they talk about geometric series underneath. And yeah, so they've got exactly the same thing here. We've got the $12,298.73, and then the summation of the geometric series is happening just after that, the plus 200 times by the thing inside the brackets. And that gives us the total amount in the nearest dollar, and then they've taken off all of the amount that was put in the first place. So over that period of 7 years, the amount of interest which has been gained, the total interest, the total extra, is $2,431. In terms of realistically here, it would be pretty amazing to get 3% in today's financial markets. You would be extremely lucky, to be honest, to get a guaranteed income of 1% per year currently. Obviously, these things change, but 3% would be really good. Okay, so a little bit extra then, because I talked about creating a model for 26 Part B. Now, 26 Part B, let me just steal this stuff here. So have a look at B downwards. So a little extra on this one, really. They came up with, this was the first 6 months, this rate of increase of 1.03. That's the common ratio, or 3% increase each year. And this is the second 6 months, and this is the third period here, the last 12 months. And we're talking about the Facebook increase in users over that period. Now, I thought it would be kind of interesting to see what that looks like on a graph. And in order to do that, I needed to set up a function. Let's actually just steal this again. I've got a bit more space. Okay, so I thought it'd be kind of interesting to set up a model, in this case, like a piecewise function. And I thought I'd put in f, the function of the number of weeks, and split this up 3 ways. And we know to start off with, we have 1.45 times by 1.03 to the power of n, where n is the number of weeks past 2000 and start of 2008. So I'm going to set this one up and say, well, n is between 1 and 26 in this case. And then for the next one, we start at 313 million. You could be more precise than this, but I'm just doing this approximately. So 313 million, I know this is rounded off, but 313 million times by 1.011 to the power of, now we can't say n here because we now need the months 27 to 52. Now, because I want to times the 313 by this only once to get to the 27th month, I'm going to need to take away 26 there. So for the next answer, or the first answer in this next period, I'll need to take away 26 from 27 there. Okay, so you might know this as well as transformations of graphs. So that basically transforms that graph by shifting it 26 months further forwards. Okay, that's essentially f of n minus 26 would shift the graph 26 forwards. You might be aware of transformations of graphs already. Okay, and for the next one, we're going to do something similar. So we've got 416 times 1.0075 times n minus, and this is between 53 and 104. So we're going to do n take away 52. Okay, now I probably should define here as well, just at the end somewhere here, n is a natural number, so n belongs to our natural numbers here. Or you could say n belongs to our positive integers as well, if you wish to be saying the same thing. We can say positive integers. And because we've defined n here as a natural number, and because we've also got this here saying that we're going from 1 to 26, we could have just said n is integers, to be honest. We don't really need the plus, but n is an integer. It's not any number in between those integers or whole numbers. Okay, so either of these, any of these would have been good things to have said there. You could have even have said n belongs to integers because we've got this extra condition here as well. Right, okay, so I've come up with this on Desmos. Now, Desmos is working here online. I mean, if you haven't used this already, it's a fantastic little resource. So because we've got a continuous axis here and we're using X on the bottom instead of N, I've just done this in terms of a continuous distribution. So I've done from 0 to 26, and then after 26 months up to 52, and 52 to 104 there as well. And there we go. I've just typed in the functions which I've just created. Instead of using X, I've used N, I've used X. And you can see what the graph is looking like here as well. So if I got rid of my condition at the end here, let's just get rid of this. You can see that that was the original assumption. And up at, let's just put in y equals 3 billion and something, or 3 billion 136, I think. At this point here, this was what you'd get after 104 months. Okay, that was the original prediction if the increase in users continued at the rate of 3% per week. Remember, that was part A. Okay, but you can see that the model was actually much more like this. So let's just put Control Z. There we go. We've just got this one back. And so there we go. You can see that this is the model, and this is what it looks like now. Do you think that's a particularly reasonable model? From my point of view, I think it would be more sensible if the model kind of went up like this. Let's just steal this. Okay, let's just take this one here. Now, I think it would probably be better if you were creating a model in a piece of coursework or an IA, which said, actually, should do something like this, some kind of curve. Okay, maybe we could get some information in the middle here, but some kind of curve that goes through those points. Now, it looks to me like it's not even a particularly good model here, because if you went through there, you get a curve which goes something like this instead. So I'm not sure this is a particularly good model. I would try and make some kind of curve in this case if I was going to make a prediction as to what was happening in between. But maybe there's actual data which you could use there. In terms of making that, now that's obviously not showing exponential growth because exponential growth is this way round. So just to talk a little bit more about this, I'm not going to do it all. Let's just put in another Desmos screen here. If I was going to make a curve like that, I might look to doing something like this. Let's use 2 to the power of something or other. 2 to the power of x. We can see we've got an exponential model like this. If we put a minus in front of this, it's going to turn it upside down. That's still no good. If we put a minus in front of this, it's going to reflect it in the y-axis. Okay, so if I do a combination of a reflection in the y-axis and a reflection in the x-axis, I'm getting kind of like the shape of graph that I would want. Now, I could maybe change that original number. Maybe I could change it to 1.1. It's making it a bit flatter. Make it 1.2. Or maybe it's make 1.5. I don't know. And obviously, we want that to be higher up. So we can put a plus something on there as well. Let's put it up. Okay, and now you can see we're getting a kind of model which we might be interested in. But in some brackets here, we might say this is between 0 and, now I know we've got between 104 months, but let's say between 0 and 8. We're just doing a kind of example, 0 and 8 there. Okay, so there we go. I mean, if you wanted to just stretch that whole thing as well, you put some brackets in front of everything. Brackets there. Maybe not the best thing to do, but let's just try it out, see what happens. Let's put a 2 in front. That stretches it all. Maybe I don't want to stretch all of it though. Maybe I only want to stretch this thing here. See what happens if I put a 2 in front of there. Okay, so it's making it kind of steeper. Let's put a 4 in front. I can change this number again. Okay, so you can see I'm just sort of playing around at the moment. But I could play around and try and match that graph, or I could do it more algebraically, and we may look at that kind of thing later on as well. But you can see that a model which is looking more like this would perhaps be more sensible than the model which looks like these kind of pointy growth things here. Okay, I'm running out of words here. Thank you for listening in. Thank you for listening to some of the extra here. And just need to stop this one up. And I'll do 1E next. Guys, have a go at the questions, of course, and cheers for listening in.